So today we are going to learn how to write the main VHDL model and test bench VHDL model for a 3:8 decoder, also known as 3 line to 8 line decoder with active low enable. As we see in this block diagram, the decoder has 3 inputs ABC and 8 outputs D0 to D7, and it has one active low enable as shown, which means when this pin is connected to logic 0, then this system acts as a 3:8 decoder, which means for every combination of the inputs ABC, one of the 8 outputs will have a unique value while remaining 7 will have same values. So if this decoder is a decoder with active high outputs, that means for En equal to 0, for ABC equal to 0, 0, 0, D0 equal to 1 and D1 to D7 equal to 0. For 0, 0, 1, D1 is equal to 1 and D0 and D2 to D7 are 0. Similarly, for A equal to B equal to C equal to 1, that is 1, 1, 1, except D7, all the outputs from D0 to D6 will be 0. And for En equal to 1, the chip will be disabled, and we can program the chip such that for En equal to 1, the outputs D0 to D7 will either be all 0 or all 1, or they can also be programmed to be in the Z state. So this truth table of decoder or operation can be represented by this table. We can see that En is the enable input and A, B, C are the decoder inputs, and there are 8 outputs from D0 to D7. Because our decoder is a active low enable decoder, that means for En equal to 1, the inputs ABC are don't care, and all 8 outputs are tied to either all ones or all zeros or high impedance state Z. While for En equal to 0, for the combinations 0, 0, 0 to 1, 1, 1, we can see that the outputs D0, D1, D2, D3, D4, D5, D6 and D7 are 1, while all other 7 outputs are tied to 0. So this is the truth table of a 3 line to 8 line decoder having active low enable and active high outputs. Now we go to Xilinx ISC and start making the model. File, new project, let the name be decoder 38, Control A, Control C, next, next, finish. Keep the tool in implementation mode, go to target line, right click, new source, VHDL module, paste the name decoder 38, reselect. Next, change the architecture name to entity name underscore ARCH. Here we will use a vector A for representing the 3 inputs of the decoder, and the vector D which will be 8 bit for representing the 8 outputs of decoder, and En will be the enable signal. So enable the input A, which will be 2 down to 0, and output D vector 0 to 7. So tool will write this signal D as the type output, and it will be 0 down to 7, but because as per the language grammar, to the right of down to keyword, there has to be a value which is smaller than the value written to the left of down to. We will change it after the model is created by the tool. Delete all comments. We'll go to the logic section and we want to use the behavioral modeling style. So keyword process, parenthesis sensitivity list. We'll write all input signals in this list separated by commas, en, comma a, begin. First we will define that when en is equal to 1, all outputs are tied to high impedance state. If en equal to single quotes 1, then output d is assigned others get z, which means that all 8 outputs of the decoder will be tied to high impedance state, and we are using the keyword others, which is called as aggregate operator. Now we come to write what should be the behavior of the system for en equal to 1, which is represented as else. So else we can use case statement here. Case a is, and we can write when 0 0 0 equal to greater than, means then when 0 0 0, then d is assigned, right? D0 has to be assigned a 1 and all other bits should be assigned 0. So we'll write d is assigned parenthesis 0 less than equal to single quotes 1 comma others get 0. Copy this statement and paste it 7 more times. 1 2 3 4 5 6 and 7. This becomes 8 combinations. 1 2 3 4 5 6 7 8. Change it 0 0 1 1 0 1 0 2 0 1 1 3 1 0 0 4 1 0 1 5 1 1 0 6. And instead of writing here 1 1 1, the syntax for case statement says that for last possible combination write others. Write it 7. Now we will end the case construct by writing end case. Then we will close the if clause and then we will close the process. So let us see if there are no synthesis errors. Save, select MVM, go to synthesize, right click, say run. So as we said on line number 9, we have defined the vector d in a wrong way. We should write standard logic vector 0 to 7. Yes. So it has been, our MVM or main VHDL model has been synthesized successfully with no errors and no warning. Let us see what are the schematics available. ITIL schematic. Close this. View technology schematic. This is how the 3-state decoder with active high outputs and active low enable will be implemented inside the selected FPGA. Now we will write the test bench VHDL model, changing the tool from implementation to simulation mode. Select target line, right click, new source, VHDL test bench. You can copy this, paste it here, change the name to _TB, reselect, next, next, finish. Delete the comments, delete, remove the clock period statements, remove the clock generation process. Now delete these lines from the skeleton of the process. Rename the process label to simply input A. Now if we see the truth table, we see that the inputs are changing from 000 to 111. Basically they are getting incremented by 1. So we can write this particular behavior in this way, is we can simply write A is assigned A plus 1 and increment this every 10 nanoseconds. But because on line number 47 we have a signal A which is belonging to standard underscore logic data type, and we are trying to increment the signal by 1, and in VHDL when you don't enclose any value in either single quotes or double quotes, that value is interpreted as integer data type. So just like in C, we cannot add two values belonging to two different data types. We cannot add the integer 1 to standard logic data type. We have to do data type conversion. So we can add one library statement in library section as use IEEE dot standard underscore logic underscore unsigned dot all. Control S, and we can initialize the signal A to 111, and here we haven't written a process for En which we are supposed to write. So we can copy this process and paste it, and we can rename it to for En. And here on line number 24 En has been initialized to 0, that means it is in the enable state. So we can write En is assigned 1, but we can wait for say 100 nanoseconds. So En will attain a value 0 from 0 to 100 nanoseconds, then it will attain a value 1, and we will keep the value of enable equal to 1 for 30 nanoseconds, and then we can have enable again as 0, and we can have it wait for infinity. So our decoder system will remain enabled from 0 nanoseconds to 100 nanoseconds, after which it will remain disabled for the next 30 nanoseconds, then it will again get enabled from 130 nanoseconds till infinity. Select the TVM, expand, run check syntax, and we can have the simulation run. Float, zoom to full view, expand the signals. We can see here that when decoder input A is equal to 0, 0, 0, only D0 is 1 while all remaining outputs are 0. For A equal to 0, 0, 1, D1 is 1, all remaining outputs are 0. 0, 1, 0, D2 is 1, 0, 1, 1, D3 is 1, 1, 0, 0, D4 is 1, 1, 0, 1, D5 is 1, 1, 1, 0, D6 is 1, and for 1, 1, 1, D7 is 1. Again at 80 nanoseconds, A again changes to 0, 0, 0, and as we know, till 100 nanoseconds the decoder is enabled. So again for 0, 0, 0, D0 equal to 1, 0, 0, 1, D1 equal to 1. At 100 nanoseconds, our enable signal changes from 0 to 1 and our system gets disabled. And as we have programmed, we can see from 100 nanoseconds to 130 nanoseconds, En equal to 1, decoder is disabled, and all 8 outputs of decoder are in Z state. We can see here. So ISIM represents the Z state with blue color and 0 and 1 with fluorescent green color. Now again from 130 nanoseconds till infinity, En is equal to 0, decoder is enabled, and we can see here that at 130 nanoseconds input A is equal to 101, which corresponds to decimal 5, and we can see that D5 is equal to 1, 110 D6 is equal to 1, and 111 D7 equal to 1. So thus the simulation waveforms show that our main VHDL model is functionally equivalent to a 3-line to 8-line decoder with active low enable and active high outputs. Thank you.